So we are recording now. So the first thing is that we will analyze the velocities of a mechanism. One thing is that very important is that the positions in the mechanism must be, let's say, determined beforehand. So, which means that the position analysis must be done, okay? Done before we start the velocity analysis. So what we have is the, as you know, loop equations, okay? Remember, we have the loop equations, vector loop equations, with lots of e to the I theta terms on them, okay? And what we were doing is we were trying to solve them to sometimes to get the positions. Well, the easy way or the systematic way to get the velocities is take the derivative, time derivative of the loop equations. Okay, and we get the velocity loop equations out of that. And this makes things quite much easier. And from these velocity loop equations, we can solve for the necessary velocities. So let's say velocity or angular velocity variables. Now, the thing is the following. The velocity loop equations are easier to solve, okay? The reason being, let's say that these are called VLE, velocity loop equations. VLE are linear in terms of velocities. Which means that linear equations are easily solvable, which is because you can use linear algebra, things like matrix things and so on. Whereas the position equations, if you remember, were nonlinear in terms of the positions. They were harder to solve. I will start with a simple example here. The slider crank example. Okay, let's say that we have a revolute joint here, and then we have a, let's use some. So we have S14 is the position of the slider. Theta 12 is the angular position of the crank, and A3, AB is the connecting rod. Now, the velocity variables here are omega 12 is here, the omega 13 is there, and then there is the velocity variable, whatever. Let's say that S14 dot. Okay, that's supposedly a dot. Let me it's here. That means the time derivative. So these are the velocity variables, the one I have drawn in the red color. So the loop equation as you know, is A0B plus BA. This is one possible loop equation. A0B plus BA is equal to A0A, for example. Okay. So we can write the following. A0B. A0B is S14 plus, this distance, the eccentricity, we call it C, let's say. So it is S14 plus IC. This is A0B plus BA. BA is A3 e to the I theta 13. Okay.
Jam, I have a question.
Yes.
When you're forming the loop equation, can the loop equation be like A0A plus AB is equals to AOB?
That's one possibility.
So there are multiple possibilities, right?
Yes. The only thing is the following. If you say A0A plus AB, then you have to measure the angle from here. This must be your angle. This must be your theta 13. Okay, which is this theta 1, let's say call it theta 13 prime. Theta 13 prime would be theta 13 plus pi. Okay, as you see. But you have to do it this way. That is, the angles are always measured counterclockwise. That's our convention, and you have to stick to that. Do you understand?
Yes, Jam, thank you.
Okay, so this is the way we did it this time, but there is no reason that you can do it otherwise as well. You'll get the same result. So this is one equation. We can use the conjugate of this equation, as you remember. We did it for the position analysis as well. So S14, instead of I, wherever we see an I, we put a minus I here. So this is the conjugate of that expression. Okay. Well, it doesn't matter. Conjugate, we will use that, but we will basically this is the from here you can solve for the positions, as you might remember. Position analysis means solve for S14 and theta 13 given theta 12. Okay. The problem is it can be done. Actually, we have done that, but it requires, as we have said, nonlinear equations, solving nonlinear equations. Here we are going to solve for x. Well, we assume that theta 13 and S14 is given. So this is done, position analysis is done, and theta 12, theta 13, S14 are known. Okay, somehow. Now we will do the velocity analysis. What we do is the derivative of the loop equation. And it will give us the following. I'll just take the derivative of this equation, okay? S14 plus IC plus etc. etc. It will be the following. It's in a different page, but you can follow. It is S14 dot. There is IC, but C term is a constant, so it doesn't enter the equation, plus I theta 13 that is omega, well, I should say 13. Omega 13 is theta 13 dot e to the I theta 13 is equal to I, this was A3, right? A3. A2 okay. Remember that we had omega 13 is theta 13 dot, okay, and omega 12 is theta 12 dot. Okay, this is the normal equation, the regular, the conjugate of that is still valid. You can also take the derivative of the conjugate, plus, not plus, minus I 3 minus I 3. We have two equations, as you know. Now, these equations actually physically mean something. If you remember, let me briefly draw it here. This was A0. This is A. This is B.
Hocam özür dilerim. Conjugate kısmında sol taraftaki kalan kısımda omega 2 olmayacak mı?
Olacak. Ben onu yanlış yazmışım. One, two.
Hocam omega kısmı da 1-2 olmayacak mı acaba?
Evet. Thank you.
Teşekkür ederim.
So what is this? If you look at this equation, this part S14 dot, this is S14 as you remember. VB, the velocity of point B is S14 dot. So this term is VB, okay? Well, what is this I A2 omega 1 2 e to the I theta 1 2. Let's try to remember this. If you had a fixed thing like here, let's say this is A0, this is A, and this distance is A2. And if you are rotating this with omega 1 2, you would know that this velocity of point A, VA would be, well, if this is theta 1 2, exactly this thing. It will be A2 omega 1 2. This is the magnitude, I e to the I theta 1 2. Okay, this is the magnitude, and this is the unit vector. Okay, so this part we say is VB. This part we say is VA. But what is this part? It is I omega 3 e to the I theta 1 3. Well, try to remember it from dynamics. That part is the relative velocity of E with respect to A. It is something like this. If A were fixed like this, if this is A and if this is B, and if this rotates with, let's say, omega 1 3, what was it? Let me check the direction. This counterclockwise. Omega 1 3. This is looks like B. Okay, in this case, the velocity of B with respect to A would be relative to A would be what? A3 omega 3, right? This is the magnitude, this is the direction. So this thing would be, just a second, I think I made a mistake there. This should be, if VB plus, this should be, okay. It should be VA relative to B. Let me erase all this, sorry about this. This should be VA relative to B. So, it should be like this. It's the same thing, but with a negative thing. This is B. This is counterclockwise. Omega 1 3. This is 2. This is okay. Sorry about this. And this is perpendicular. This is also perpendicular. And this will be VA relative to B. Okay, there is a physical interpretation. VB plus VA relative to B is equal to VA. Okay. In a way, you can say the following in terms of the vectors. VA, this is directions of, let me draw it in red. So VA is like this. Then you have we know the following. Let's say we know VB. Then you have yes. VB has to be in this direction definitely, but how do I? VA relative to B. But let's do it later on. So we can write VB plus VA relative to B equals VA. Okay. Or we can actually write VA plus VB relative to A is equal to VB. And we know that VB relative to A is the negative of VA relative to B. Okay. For example, we can write S14 dot, which is VB, is equal to IA2.
I'm sorry, but could you go back for just a minute?
Yeah, okay. Just a second. Let me write this down. Yes. Yes, you can ask your question.
No, Hocam, that was the question you
Oh, you are just trying to write. Okay, sorry. So this is VB. This is VA. And this is VB relative to A. And it has a minus sign because this is minus VA relative to B. These are all vectorial, of course. So we can, in a way, say the following. Let's say that this is VA. This is VB, okay. And this will be. This is called the velocity triangle for this system. So in this velocity triangle, as you know that omega 1, 2 is given, S14 dot theta, it's not theta, omega 1, 3 to be found, let's say. So if omega 1, 2 is given here, theta 1, 2 is already given, this is known. Okay. What else is known? Theta 1, 3 is known. Well, I theta 1, 3. So here we know the direction of this. Known. And for VB also we know the direction. But not the magnitude. So what you can do is you can draw a VA vector graphically, and you can, since you know the direction, you can draw this thing, okay, which you don't know the magnitude, but then you know the direction of VB, which has to be like this. So their intersection will give you the following. VB and VA are absolute vectors. So they start from a common fixed position. But VB relative to A is a relative vector. So it starts from A and goes towards B. Okay. In the velocity triangle. Okay, so I tried to here give you the graphical geometric solution, which gives you more insight to the problem. But what we usually do, oh, sorry, not I should not do anything. Oh, let's say. Let's go to the previous page. We have written this thing down. We can use these equations actually to solve for our unknowns analytically. So the analytical solution is as follows. Let's say, let me write this down again because what was it? Okay. So we have two equations, as we know. We can use them to solve for our unknowns. Let's say our first equation. This is our second equation. Now, notice one thing here. This is actually a matrix equation, okay? Because I can write it as follows. 1 I A 3 omega 1. So these are the unknowns, and this part is a known thing. So how can we solve this? We have to just invert this matrix. It has complex quantities in it, but it doesn't matter really. We can solve for this. Let's say use Reiner's rule to solve for it. And for example, I can say S14 dot will be the following. Now the determinant of the matrix itself, I, A, 2, 3, whatever that is. That will be a determinant. So I will just put a determinant here. And this determinant is going to be IA2 omega 1 2 e to the I. Okay. Two determinants, you multiply them with each other, and the result is going to be, well, a long expression, but it can be simplified. I's multiplied to get I times minus I gives you a minus I squared, which is 1, for example. So you get A2, A3 times e to the I theta 1, 2 minus theta 1, 3 here. This multiplication minus e to the minus this can be, for example, in this parentheses. Now you can now see that we will probably use some trigonometric identities here, and this multiplication will give you I minus A3 Okay, remember the trigonometric identities. What was it? Cosine theta was e to the I theta plus minus I theta over 2. Sine theta was e to the I theta minus e to the minus I theta over 2I. Okay. All these can be used here. For example, this looks like a sine term with a minus I here, etc. So you will get S14 dot is going to be is There has to be an omega 1, 2. Eventually, you get minus A2 and 2's cancel. Sine one minus 2 divided by cosine theta 1 2 times omega 1 2. That's one solution. And let me solve for omega 1 3 as well. That determinant divided by this determinant. Okay, I'll just say same as above, which means this. Okay, this. I don't want to write it again. And if you do it, if you do this, you take the determinant, what you are going to get will be minus IA2 e to the I theta 1 2 plus e to the minus I theta 1 2 divided by minus IA3 1 2 plus and if you again use the trigonometric identities, let me write it here. Omega 1 3 can be written as A2 over A3 So these are the solutions, the things I have put in brackets as you see here. Okay. Now we did it by doing taking the conjugate as another equation. Actually, we could do the same thing, exactly this. We could obtain the same result, you know, taking this equation that we had. What was it? The original loop equation derivative, separate it into real and imaginary parts. Okay, because we have actually two equations here. a real equation and imaginary equation, and solve for the unknowns using the real and imaginary equations, we would get exactly the same result. There would be no difference. Okay. You could try it yourself if you want. Maybe that might be a little bit easier, but again, you might need to use some trigonometric identities for that. Okay. If you don't have any questions, I'll take a break at this point. How do I do that? Resume recording. As I have said before, let me write it down. We can get the same result. Let's say if well, actually, I have informed you about it, but probably you were not there. We separate real and imaginary of BLE. Let's see. Okay. This is an example for velocity analysis. It can be, it gives you a systematic way, as I have said, to obtain velocities. And as you see, the velocity equations are linear, meaning that although they look complicated, you can put them in matrix form. If you can put them in matrix form, it is possible to solve them. No matter how complex they are solvable. Whereas the nonlinear equations are kind of harder to solve because of other reasons. Okay. There is one more thing in the velocity analysis. Let's say I'll very briefly draw the slider crank again. I'm not, why am I using it? Let me use my pen. You might want to find the velocity of a certain point. Let's say, for a strange reason, you might want to find the velocity of this point C. Let's say this is A0, this is A, this is B. Okay. This distance is, well, it's the eccentricity. Let's call it E this time so that we don't mix it up. call this alpha. And AC distance, let's call it C3. We can write, for example, position vector of C can be written as A0A plus AC, or that can be written as A2 e to the I theta 1, 2 plus AC is, what is AC? If this angle is theta 1, 3, okay, theta 1, 3 minus, yeah, it will be C3 times e to the I theta 1, 3 minus alpha, for example. Okay. For that plus alpha. Plus alpha. Why? Because we have, this is theta 1, 3. On top of that, we have alpha. Okay. So we can say, for example, if this is RC, BC is the derivative of this, which will be I A2 omega 1 to e to the I theta 1, 2 plus I C3 omega 1, 3 e to the I theta 1, 3 plus alpha. Okay. Now, once you solve for, let's say, after solving for, let's say, omega 1, 3, we can we see. Another possibility is, for example, you can use some other, let me do it somewhere else. Let me draw it here. Let's use the C also. But here we can use, for example, this is theta 1, 2. Let's say that let's call this angle gamma. Let's was alpha, as you remember. Here, for example, we can also say the following. RC can be written as,
John, isn't theta 13 up till A3? Theta 13 includes gamma as well, right?
theta 13, this time I counted up to B3 line, okay?
Okay, John.
In this case, for example, we can write, if this is S14, RC can be written as S14 plus IE, okay, which is the eccentricity, plus B3 e to the I theta 13 minus gamma, let's say. Okay. An external angle. Yeah. So VC can be written as S14 dot plus I D3 omega 1 3. I'm just taking derivative e to the I theta 13 minus. This is another possible solution. Another possibility, let's see. What I mean is, we can find the after solving for the loop equation, we can find the velocity of any point inside the mechanism by using these vector relationships. Okay. Let's keep this in mind. Now, let's go to the now a little bit to acceleration analysis. We will try to obtain accelerations of mechanisms, and what we do is we to obtain accelerations, it's very simple. We, in principle, it is very simple. We take the derivative of the loop equation. Okay. That is, remember the velocity loop equation for slider crank again. The equation was, what was it? S14 dot plus RA3 theta 13 to the I theta 13 was equal to IA2 Okay, we will just take this equation and we will take its time derivative. Well, it will be more complex, but still it will be a linear equation. That's the good thing about it. Let's do that. S14 dot derivative is S14 double dot minus. Now we will use chain rule. There are two quantities. Omega 13 is a variable. Theta is a variable. So we will use the chain rule to take derivatives minus I A3. Well, omega 13 derivative, let's use it alpha 13. e to the I theta 1, 3. Then we have the derivative of theta 1, 3. It will come here and it will multiply, I will multiply I to give you a minus sign. I squared is a minus 1. Oh, this is a plus, by the way. This is a plus. Minus A3 omega 1, 3 squared e to the I theta 1, 3 is equal to, but again we have a multiple derivative chain rule, I A2 alpha 1, 2 e to the I theta 1, 2 minus A2 omega 1, 2 squared e to the I theta 1, 2. Okay. There is a physical explanation actually here. Here this is acceleration of B. This whole thing is acceleration of A relative to B. Okay, and this is, let me just do it. This is A relative to B. And this whole thing is I'll come to its parts. This is AA. Its parts are, this is A relative to B, the tangential component. And this is AA relative to B, the normal component. And this is AA, the tangential component. And this is AA, the normal component. Okay. Well, this is one thing. What we can do is separate it into real and imaginary parts, again, this equation. So write it in terms of sines and cosines, or you can use the conjugate of this. Let me write down the conjugate. Your book does that, so let me. Well, many mistakes, of course, here. I think it's correct now. This is the conjugate part. But what are the unknowns? Again, we have one given and two unknowns. By the way, this is important. The velocity analysis must be done beforehand. which means that certain quantities like omega 1, 3 must be known. Also, S1, 4 that must be known, but it's not necessary here. But here, omega 1, 3 is necessary. Now, if you look at these two equations, this one and the conjugate of it, these equations are linear in alpha 1, 3 and S1, 4 double dot. They are very complicated, but they are linear. So it is possible to solve for these quantities. I don't want to write the details because it really takes a lot of time to write them and solve them and so on. Basically, we can express them in matrix form and solve using, let's say, again, Kramer's rule. Okay, it's not too hard. I'll just write down the solution for you here. Even writing the solution is long. Alpha 1, 3 now is going to be this long expression. A2, alpha 1, 2. The acceleration of the piston is the following. Alpha 1, 3 is in the solution because otherwise it becomes too complicated. Alpha 1, 3, we assume it is solved above. So sine theta 1, 3 plus omega 1, 3 squared cosine theta 1. So these are the solutions. Remember that this is for the slider crank. Let's try to remember what we were doing. This is what we have. It's a slider crank with some eccentricity. So this was And we had some eccentricity, which we will call, which we had called C, I think. Now we try to find the accelerations. This is A2. Acceleration of A has a normal component. And it has a tangential component. Acceleration of B is like here, A, B. It can be in either direction, positive or negative. Now we have acceleration of B relative to A. That has a normal component. It also has a, sorry, not like this, tangential. And as we know, we can write AB is equal to AA plus AB relative to A, which can also be written as AA tangential plus AA normal plus AB relative to A. Let me try to draw this for you using some vectors. So this is something like AA normal from here. Okay. Then we have perpendicular to that some AA tangential. Let's have it a little bit longer. Eventually, AB is going to be something like this. This is what we are going to aim at. AB relative to A normal will be something like this. This is AB normal. And then perpendicular to that is going to be AB relative to A tangential. And finally, this whole thing is going to be AB. Okay. So this is called the acceleration polygon. In a way, you can draw it as a triangle as well. For example, this AA normal and AA tangential added up gives you AA. Okay. And AB relative to A normal and AB relative to A tangential gives you AB relative to A. So AA plus AB relative to A gives you an AB. Okay. That is the graphical interpretation of this whole solution. You know, you can just solve all these equations, but it is better if you have an understanding of what you are doing here. Oh. Again, for the acceleration, we can find the solutions on the coupler on any point. So again, let me draw this thing again for a while. Let's say that we have a coupler point like this one. Let's say this is point C. This distance is B3, this is C3, this is A, this is 0, this is B, 2, A, 2. So for example, again, you can write, this distance is B, you can write RC is equal to, let's say S14 plus IE plus B3 e to the I, take the 1, 2 minus gamma. So the velocity of point C is going to be the derivative of this. That's one, so that plus omega 1, 2 e to the I. Okay. And the AC is going to be the further derivative of that. As a matter of fact, there is a interpretation. This is AC again. This is AB. And this whole thing is A, C relative to B. As we can see. So physically, we can interpret that. So once you solve for the mechanism using the loop equations, you can always get the solution for any point. That's called the C point is in the mechanism language. C is called the coupler. So we have done the velocity and acceleration analysis for a slider crank mechanism. That's all we did today, but it was usually we tried to be kind of instructive here. Well, we will continue with 4-bar and inverted slider crank, etc., and possibly with some other mechanisms. The idea is clear. Although it takes a long time to solve, the velocity and acceleration analysis for mechanisms is straightforward because the equations are linear. The equations come out to be linear in terms of the unknowns. So you can use the rules of some linear algebra, which makes it systematically easier to solve. But of course, it might take a lot of effort to do that. And on the other hand, you should be aware of what you are doing. Okay, you cannot just automatically write the equations and try to get the solutions. If you know what you are doing, usually you avoid the mistakes. If you try to do this by hand, you almost always make a lot of errors. Okay, there is it's very common to make errors in these calculations. So if you know the physics of the problem, at least you can go back and try to find out those errors. Okay, so much for today. I will continue, as I said, with the 4-bar and other examples. So let me stop the recording.